full screen.
Oh, okay, yeah, that's in focus.
Yep. Hi everyone. I am Tintin Liu, a second-year PhD student. Thanks for the great introduction. And so today we are going to learn, probably remind you something that you probably already learned. It's linear algebra in calculus. Algebra in calculus. Hopefully you can see the screen well. Okay. Am I allowed to sit? Yeah?
Autofocus freeze button, so it's not autofocusing all the time. Autofocus lock, this thing. Once it's in focus, which is not right now. Now it's in focus.
Yep.
So hit this autofocus lock, and that will lock it, so it will not be refocusing all the time.
Great. Great. Okay, so I'm gonna start with something you know. It's let's take the derivative of a function f. So now f is basically a scalar function. It takes a scalar vector and map it to another scalar field. So if I draw it in 1D, so this is my variable x, and this is my function fx. It could be basically anything. So and this is my function f. Okay, so now what's the first order derivative of f? As we know, we just defined f prime x as a limit of x approaches to, sorry, I can have, if I want to get the first order derivative near point A, I can have this formula, fa plus f. The derivative near A is the limit of x approaching to 0, f a plus x minus fa divided by x. So what does this mean? This means that if I have a linear approximation near the function f at the point A, then I can have the slope of this function. So we can write it in another way. So basically f prime A, we can define it as the total derivative of f at A. So this is one function. I'm gonna have the parentheses of it, and I will use this notation a lot in this class because this notation can be easily extended to those high dimensional cases. Okay, so once we have this notation, we can also represent f a plus x is approximately equals to fa plus the total derivative of f near point A multiplied by x. So x will be a really small region near A, and we can represent fx equals to this thing. So that means that in the calculus interpretation, this first order derivative can be seen as the optimal local linear approximation of f. So we can basically linearize my f function into different line segments, and basically the slope of those lines is are the total derivatives near those points. Okay, so basically this should be covered in your undergrad calculus class, and what I want to mention is what is the geometric interpretation of the slope of this thing. So this is a scalar. It has a sign of the scalar and have the magnitude. How to spell it? Okay. So the sign of the scalar is either positive or definite or negative. If it's positive, it means that the function is increasing around this point. And if it's negative, like if I choose another point here, then the first order derivative should be negative. And negative means that my function is about to decrease at that point. Or I can say it in another way. If the function wants to increase, then negative slope means that I need to decrease my x to get the function increasing. And also here we got the same thing. If I increase the value of x, then the function will go up. So the sign of the scalar, the sign of the first order derivative of the function means that this is which one is my ascent direction. If the function wants to go up, which direction should x go? And the magnitude means that how large the slope it is. It means how eagerly the function wants to go up or go down. Okay, so this is the geometric interpretation of the total derivative x, of the total derivative over f near the point A. Yep.
You want to zoom in so it's a little bit bigger.
How do I, this one? Does that look better?
Yeah.
Okay, cool. So this is a definition of the total derivative in 1D. And let's see some standard calculus rules about this 1D first order derivative. The first one is factor rule. So if there is an alpha also belongs to R1, so what is the first order derivative of alpha f? So we can basically get it out. It's an alpha multiplied by the first order derivative of f. Is that true? Imagine there is a function fx equals to x squared. If I multiply the function by 2, which is the 2fx, this is a 2x squared, then the slope of each point will be doubled. So this is basically the factor rule. And the second one is a sum rule. So if I have another function g, which is also a map from R1 to R1, the total derivative near point A of f plus g, and I can just expand it out, is the sum of the total derivative of x and g individually, and sum them up. So basically, those two rules tells you that the first order derivative of a function is basically a linear function. And the third one is a product rule. Also, we have a function g maps from R to R. So what is the total derivative of f multiplied by g? So this is more complicated. To me, this is where calculus starts. And so anyone tells me what's the answer of this equation? By f. Is that true? Is that what you're saying? Or I can write it another way. It's f multiplied by the derivative of g. Wait, is this right? Because this is both of these are scalar functions, so I can just commute them, right? And the last one, which is I think it's the most important rule when I was doing this calculus class. It's a chain rule. So still, I have a function g, which is a map from R to R, and define a new function h, which is f compose g. So what function h does is hx equals to f of gx. And so I want to get the total derivative near a of h, which is f compose g. And we can simply apply the chain rule of it. So it's the derivative near point GA of function f multiplied by the total derivative near point A of G. All right? So those things, I assume you are really familiar with it, and so I'm going this very quickly. Do you have any questions about the calculus in the scalar functions? Yep. You mean this one? It's a composition. So basically, the definition of composition is like this. It's just a circle, right? Oh yeah, there's also a quotient rule, but for now, for me, it's a little bit complicated to extend it to 3D or even higher dimensions. So if the quotient rule is if there's a g goes from R to R, then the this function f divided by g, this one equals to what? You don't know that? Probably I also forgot. Right? Yeah? What did you say?
The thing is, you don't really need this rule. It can be derived from the previous rule, right? It's just f multiplied inverse of g, and inverse is just the function, so you can apply the chain rule to get the inverse of g and the product rule.
Yep. Yep. So if you divide it up, it's f multiplied by 1 over g, and you can apply chain rule to this thing, and also multiply by f. So basically, applying chain rule and product rule to get the result of the quotient rule. All right. Okay. So okay, this is 1D. Also this is 1D. Those are functions goes from R1 to R1. All those functions take a 1D variable into the function, and the results as another 1D variable. Okay, so now let's start this class today. Let's go into a multivariate function. So the multivariate functions f is a function that maps of a Rn space to R. So what does this function mean? For example, if there is a height field, if there's a mountain, then basically I have an x and a y. Those are two of my coordinates, and this the height field is a function of R2 to R. I have two dimensions on the ground, and I have the height as a function of my two dimensions. Or I have other dimensions like the energy of the gravity field. So this is another function maps from R3 to R. So you can just point anything in a space which is the R3 space, and then it has a potential energy caused by the gravity. All right. So this is an R3 to R function. So there's lots of things, lots of functions. Most of them are energy functions that we care about, is defined using this multivariate thing.
Did you turn on the light? There's a little light.
Really?
Yeah.
Much better? Great. Thanks. I don't know. It's okay. So we can have a similar definition of what is the total derivative of f. Here I'm gonna write an arrow over here because the total derivative of f will no longer be a scalar, it will be a vector. So if f is such a function, then I can, I'm just gonna repeat it to a column and treat the first function as the function of x1 and the second function of x2 and then x3 blah 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 to xn. So in a height field, basically I have fx and fy. If you are looking at a mountain from x direction or from y directions, there will be different functions, but they are R1 to R1 functions, all right? Okay. Wait, why the resolution becomes so slow? Okay, better? Sure. And then we can treat it as a function of different variables, saying that if I have a function f xy equals to x squared plus y squared, and then what is the partial derivative of x and y over x? This is basically 2x because I'm treating y as just a constant value. And also, I can do a similar way to get the partial derivative of y, which is 2y. So if I'm doing this for all the variables, I'm going to add, I'm going to do something to this function, get a partial derivative of all of its variables to xn, and then this can be seen as a derivative of the function. All right. So the first thing that we can see is this is a vector, and also we can write a similar equation with this one, because in 1D, as interpreted using a calculus way, a function near point A can be seen as a linear function, and the slope of the linear function is the total derivative of f. So I'm gonna just copy it down to here. So I want to get the function value near point A. So now the point A is in the Rn space, which is an n by 1 vector. And I can also approximate the function plus x using the value of the function at A plus the total derivative of f multiplied by x. All right. So so now someone tell me, what is the dimension of f? So the result of f will be a single value, all right? If you imagine the height field, then the height is just a single value. Or if you imagine the gravity field, anything in the gravity field, the energy is basically a single scalar. So f is a 1×1 matrix. Basically, it's a scalar. And also, fa is also a 1×1 matrix. And the dimensionality of x, this one, is n×1 because x belongs to the Rn space. So what's the dimensionality of the total derivative of this thing? Right? It's going to be a 1×n matrix, so the dimension will match. So it's a little bit different with this derivation that we just have, because people usually do define this one as the gradient near the function near the point A, and put this as a total derivative of f. So basically the gradient of f can be defined as the total derivative near a transpose. It's basically some notation difference. Someone just treat gradient as a row vector, then it equals to the total derivative of f. Or someone wants the gradient to have the same dimensionality with the input x. So then they just put a transpose sign over here. So the gradient will be an n×1 vector. And it also defines the best linear approximation of function f near point A. So how do we see the meaning of gradient? If I have a function, this one, fxy equals to x squared plus y squared. And let me show you a function. Oh. Okay. So this is a function of a height field of this thing. So this is basically a paraboloid of revolution. You can see if you look at this function from any direction, it's a parabola. It's basically x squared if you look from the x direction, or it's y squared from y direction. And if I'm going to draw it in 2D, like this thing, this is x and this is y, and those will be the contour lines of the function. This is x equals to 1, y equals to 1, so the function value will be 2. And this is x equal to 2, y equals to 2, and the function value will be 8. All right? And as our definition, what is the gradient near the point like 2, 2? If x equals to 2, y equals to 2, this is my point A. And what is the gradient of function f near point A? So it's going to be 2x and 2y, and substitute x equals 2, y equals 2 into the equation. It will be 4 and 4. So basically, it will be a vector that points out of this direction. All right? If I get another vector here, like -1, 1, it will be another vector points to that direction. So basically, gradient is also a vector. It's a vector. It has the direction and the magnitude. If you remember our scalar analogy of the sign and the magnitude, then the gradient is a direction and a magnitude. So the direction of the gradient is the direction that increase my function in the best way. So it's my best ascent direction of the function near point A. And then the magnitude tells you how eagerly it wants to go up. If the magnitude is small, like for -1 and 1, the magnitude of the derivative should be something like 2. Sorry, square root of 2. And it means that and the function near this point is increasing slower than the function near this point. All right. So this is basically the geometric interpretation of the gradient or the first order derivative of a function. Do you have any questions about it?
Can you just repeat the last one again? This thing again?
Oh, this thing?
Yeah.
Yeah. So the gradient of function f is a vector, right?
Okay.
And for a vector, it has both direction and magnitude. And what I just made is an analogy to the 1D case, because in 1D, a number has in 1D, a scalar value has a sign and its magnitude. And I have told you that the sign means that in which direction of x will make the function increase. And the magnitude tells you how large it will increase around this point, right? So if I have this vector case, the direction of the vector tells you what is the what's the ascent direction of the function. It's the steepest ascent direction of the function. And also the magnitude tells you that how large the ascent direction would be. All right. So how could it be used in physically based simulation and oral applications? It's actually very simple. So if this is my function, x squared plus y squared, and assume I am really stupid and I don't know what is the minimum point of this function. But I can sample around the function to get the gradient of each point. So if I sample this point, I get the gradient of this point is 4 and 4, which means if I go along this direction, the function will go even larger. And what if I go to the negative direction of this one? So this is the steepest ascent direction, so the opposite direction will be the steepest descent direction. So if I carefully go to the steepest descent direction for some steps, and eventually I will probably go to the original, which is which gets the smallest value of the function. So because in lots of functions, we don't know the explicit definition of it, but we know the gradient of it at every point. And that's how we do the that's how we are going to do to find the minimum value of the function. Yep.
Are you going to do the connection to the homework? Like this would be a good point. How to connect to the homework or assignment number 1. I can do it. So in assignment number 1, you will be computing gradient and Hessian. Hessian we will do later. And gradient is exactly this thing of Hücken spring. And the gradient of elastic energy is nothing but the forces, right? Forces is what we'll be simulating.
Right. So I'm actually gonna use another example. So let's see the gravity field. If I have an object with mass equals to m, and it also has the coordinates x, y, and z. So what is the potential energy of this object? The potential E of x, y, z equals to m, g, y. All right. So this is the potential energy of an object in a 3D space. And y is the height of the object, and the x and the z are the 2 dimensions on the ground. Do you have any questions about it? Okay. So so then I want to get the gradient of E. So we can use our definition the gradient of E is partial E, partial X, partial E, partial Y, partial E, partial Z. And this is my gradient of E around any point because they're the same. So it will be 0, mg, 0. Right? And remember, what is the force of any object in a space? The gravity force equals to negative 0 mg 0. And this is not it's not just a coincidence because I said gradient is the steepest ascent direction of a function. And the force, the gravity force, always wants to decrease your potential energy as much as possible. So it's just the negative direction, the opposite direction of the gradient, and they have the same magnitude. All right, great.
Yeah, I think I said it wrong. He's right. The force is the negative gradient, not the gradient.
Right. Okay, and I think I can move on. So once I introduce the gradient of a function, of a multivariate function, I also want to have some rules like this standard calculus rules for 1D function. So let's copy it one by one. The first one is also a factor rule. So what is the factor rule? If alpha belongs to R1, what's the total derivative of alpha f? And this one should be simply alpha multiplied by the total derivative of f. If you remember the 3D Polaroid case, it's if I times alpha, if alpha equals 2, then the original paraboloid should be like this, and if I times 2, it will become like this. All right. So that means that all the gradient will have the same direction but double the magnitude. And the second one is also the summation rule, the sum rule. If I have another function g, which is also a map from Rn to R, then the total derivative of x plus function g should be the total derivative of f plus the total derivative of g. So those two still tells you that the gradient operator or the total derivative operator in ND space is also a linear function. You can just get those constant values out and get the summation out. And let me see. And the third one is the product rule. Now it becomes a little bit more complicated. Still, if I have a g, it's the map from Rn to R, then what is the total derivative near point f multiplied by g? So I will also copy the case over here. It looks like it's gonna be this times g plus f times the total derivative of g. All right. So here, because we know that the new function f multiplied by g is also a function maps from Rn to R, so the total derivative of this one should be a n by 1 by n vector, or the gradient of this one will be n by 1 vector. This one is a 1 by n vector too, and this one is also a 1 by n vector. But here the good thing is both g and f are just a scalar. So it's a matrix times scalar plus, sorry, it's a vector times a scalar plus a scalar times vector. So the dimensions still match. All right? Okay. And 4, chain rule. So here we got a little bit of problem to introduce the chain rule into this function directly. Because now we have studied those f and g's, they can map from R to R, or they can map from Rn to R. So if both f and g maps from Rn to R, I cannot simply get a composition between f and g because it doesn't really make sense. If g maps from Rn to R, then f must maps from R to R. All right. So I can do a similar way to introduce a more complicated function. It's a vector function. It's not me like on purpose making things more complicated on purpose but the vector function also has its physical meaning. It's a function maps from Rn to Rn. Now it's a little bit more complicated to think about the function, what the hell that is. But sorry, for example, I can have a simple R3 to R3 function used in fluid simulation. Because if I have a fluid field, if I sample all those positions on the space, it has a velocity. So then I can map the position of a point with the velocity field, the velocity vector of the field. All right, so it's going to be an R3 to R3 function. Or you can think of another R3 to R3 function, which is the deformation map. If I have a very weird space, then if I put anything into the space, it will just expand the x and z direction into double. It's like if you throw a thin guy into it, it will be a fat guy. If you throw a fat guy into it, it will be even fatter. So if I put a shape this thing into I'm going to just draw it in 2D. So this is an R2 to R2 map. If I put a square into this field, it will transform my square into a rectangular. Because basically, if I multiply all the vertices by a scaling matrix, like 2, 1, 0, 0, and this is my deformation map. And this is widely used in deformable object simulation. All right, so now we know the function f, the vector function f, has its own meaning, and we want to also get the total derivative of the function f. So I'm gonna do a similar way. So function f is a vector. I can sample the vector near a point A. And here both A and X are n by 1 vectors, and the value of the entire f will be an m by 1 vector. All right? So I can do a similar way because the first order total derivative is tells you what is the best the best linear approximation of the function. So this is a function, and I'm gonna write something. This is my total derivative multiplied by x. And this will be the total derivative of f. Right? So now what's the dimension of this thing? It's still, because this is a vector function, it maps everything into Rm. So the dimensionality of this is m by 1. And what about this thing? Because x, the variable x, it's in the n-dimensional space. So it's going to be n by 1. All right? So then, what's the dimensionality of this matrix? Right? It's going to be m by n. So when I was trying to learn the derivative of the vector function, this is really important because I really need to know the dimensionality of all the matrices first, then I can derive all the functions. And also, it's a great way to see if your derivations are correct. If the dimensionality even doesn't match, then the derivation must gotta be something wrong inside it. So let's expand this matrix to see what is inside. So we can do a similar way as we derive for the gradient. We just treat f as, so f is basically a function. It has an n-dimensional spaces, so it has f1x and f2x, blah, 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 to and fmx. All right, and I can get a total derivative of those functions one by one, and finally it will expand to this matrix. Right? So what's the total derivative of f1x? So I'm gonna write it again. It's the total derivative of f1. This is a total derivative of f2, blah blah blah, to total derivative of fm. And then we can use the same thing that we derived before. All right, just to do the partial derivatives one by one. So this is a f1 partial x1. This is f2. No, sorry, f1 partial x2. Blah 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 to f1 partial xn. And for each column, it will be fm partial x1 plus partial x2 blah 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 to fm partial xn. Right? So how many rows are there in this matrix? There are m rows. And how many columns are there? There are n columns. So it matches perfectly. And this is usually called the Jacobian matrix of a vector. Or some people just call it a gradient, the gradient of a vector, but usually people just call it the Jacobian matrix of a vector. Right? And once we have the Jacobian matrix, we can go back. Where is my back? We can go back to have our chain rule for this multivariate function. So if my f is a function maps from Rk to Rm, and g is another function maps from Rn to Rk. Now the composition of x and g will have real meaning. All right. If I have hx equals to f of gx, the innermost x vector is an n by 1 vector, and after the function of g, it becomes a k by 1 vector, and after the f, it becomes m by 1 vector. So this is a real function. And what is the total derivative of h near a point A? I'm gonna write it again. So again, and I'm gonna copy this chain rule to it and see if everything goes well. The chain rule is that it wants me to have the function, the total derivative of GA of f multiply by the total derivative around point A of function g. I just copied this down to here. All right. Vectors. Okay. So what's the dimensionality of this one? This is the Jacobian matrix of G. All right. So what's the dimensionality of the Jacobian matrix of G, where G is an Rn to Rk matrix, is an Rn to Rk function? So this is a k by n. I heard someone is speaking k by n. All right. And also, this will be the Jacobian matrix of F near GA. So what's the dimensionality of this one? Right, it's going to be n by k. And you can see that the dimension here matches perfectly. And the product of those two matrices becomes a m by n matrix. Because finally, hx is going to be a Rn to Rn function. So the chain rule of this multivariate vector function just to tell you the Jacobian matrix of the composition of two functions is basically the product of the Jacobian matrices of the individual functions.
So we can say that.
Sorry. Thanks. So until here, is there any questions about all the rules in the multivariate functions? And any questions about the vector function? Any question about the Rn to Rm function? Nope. 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 Okay. And at last, I'm gonna do a special rule in those multivariate functions, because you know in high dimensional spaces there's we can simply have this thing. If f is a Rn to Rm function, and if G is also a Rn to Rm function, so it's very common to have a h function equals to f dot product G. This is a dot product. So basically, we can write it as the f transpose G. They are the same meaning. So eventually, h will be an Rn to R1 function. So this is and I want to get the total derivative of h, what it is, because it's really complicated to have the transpose sign over here, and if you directly apply the rules of our the things that we get previously, it will cost you a really long time, because maybe you need to write out the indices and to see if there are any transpose over here, over there, or something like this. Okay. But we know that this thing is a gradient of a function h near point A. It's the best linear approximation of h near A. So if I have h of a plus x, I can write it as an ha plus my total derivative multiply by x. All right. So now it seems it becomes easier, because all I want to get is this one. So what is this one? h of a plus x, I can write it as f transpose a plus x multiplied by g of a plus x. All right? And because we know the Jacobian matrices of both f and g, so we can linearize those functions at the point near a. So f a plus x can be seen as fa plus the Jacobian matrix of f near a multiplied by x transpose. And also, I can do the same for function g. It will be ga plus the Jacobian matrix of g multiplied by x. All right. So if I expand this, oh, and also because transpose is a linear operator, I can simply put it inside. It equals to f a transpose plus its transpose, so it's an x transpose multiplied by the transpose of its Jacobian matrix, and also multiplied by GA, just to copy it down, the Jacobian matrix of G near A, multiplied by x. And I can simply expand it. It becomes F transpose multiplied by G at point A plus X transpose, the Jacobian matrix of F multiplied by G A, and plus this one multiplied by this one. It's an F transpose at A multiplied by the Jacobian matrix of G multiplied by X, and also the last term. And the last term is a higher order of X, so I actually don't very care about it. I'm going to just write it as a small term. And because all I care about is the linear term of the function. And also, X is a n by 1 vector. So X transpose will be the entire X transpose will be a 1 by n vector. And also the Jacobian matrix of F, the dimensionality of the Jacobian matrix, is there a transpose here? Yeah. Right. Because I just copied it down. It says there's a transpose over there. The Jacobian matrix of F has a dimensionality of m by n. So here, after the transpose, it's going to be n by m. And well, the value of function g, it is an n by 1 vector. And what is this one? This one is a scalar. All right. Is there any questions about this? Because it's very important to see this as a scalar, because if I have a scalar c, the transpose of the scalar c should be itself. It's a 1 by 1 matrix. No matter how you transpose it, it will still be the 1 by 1 matrix, and nothing will be changed. So I can simply transpose this thing. So that one will equals to F transpose G at A plus transpose this one, G transpose the Jacobian matrix of F times X plus F transpose the Jacobian matrix of G and times X plus something small. And we can simply combine those two together. And because F transpose G is H, so this is HA, and plus G transpose Jacobian matrix of F plus F transpose Jacobian matrix of G, this thing times X. And then this is our total derivative that we want to get. Right? It's the best linear approximation of h near the point A. So why do I need to get this one? Because it's very common to see. For example, I have a really simple energy function E. Ex equals to x transpose Ax. So this is going to be a quadratic function over x, and it maps from Rn to R, and it's usually used to represent some quadratic energy. So if I want to get the derivative of E near point A, what it will be. So I can just use this equation. So the derivative of E would be G. Oh, right, and then I can think of E as the combination of two functions. The first function is fx equals to x. All right, and the second function is gx equals to ax. And now it perfectly falls into this formula because this is basically a dot product between f and g, or I can write it as an f transpose times g. So the total derivative of E is basically to say I'm going to transpose fx, so this is f transpose, multiply by the Jacobian matrix of G. So what is the Jacobian matrix of G? Anyone? If G is an Rn to Rn function. And what's the Jacobian matrix of this one? If I expand it out, it will be A11, A12, A1n. This is A21, A22 to A2n, and goes to AN1, AN2 to ANn times x1, x2, blah, 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 to xn. All right? So eventually, it will be a function, and the first element, eventually it will be a column. And the first column is A11 x1 plus A12 x2 plus blah, blah, blah to A1n xn. And the last element of the column will be AN1 x1 plus AN2 x2 plus blah, 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 ANN xn. And we can just do the same trick for it. And what's the first function? Take the partial if this is my f1x. So what's the partial derivative over x1? Yeah, it will be A11. And what's the partial derivative of the second x2? It will be A12, all right, because any other things will be treated as constant and then goes away. So it's A12. Yes?
We want to scroll down a little bit.
Oh, right. I'm sorry. Yeah, if you can't see anything, just speak it up because I don't see the screen regularly, and yeah. And what about the third one? It will be A13, all right? I can just go down to the end of the row. It will be A1n. And I can do the same trick to all other rows and columns. So the last row of the matrix will be AN1, AN2, blah, 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 to ANN. And we just realized this is basically the matrix A. And we just goes back to the matrix A. And if I take a 1D analogy of it, if I have a function G, if I have a really simple gx equals to a multiplied by x. This is scalar, x is also a scalar, and g is also a scalar. What's the total derivative? A is probably not a good idea. What's the total derivative of g? It's basically a, all right? Because this is the first order derivative of gx. And also, we can extend this idea to also this thing, because you can see ax is a linear combination of it. Since ax is already a linear combination of it, what's the best linear approximation of it? It's basically a. So a is its Jacobian matrix. All right? Yep. And also, we can do the same trick with f. We can also get the Jacobian matrix of f equals to x, because x can be seen as a large n by n identity multiplied by x. So this is already the best linear approximation of the function f. So the Jacobian matrix of f here is basically identity n by n. Okay, so let me write it down. Here, I want to get the f transpose multiplied by the Jacobian matrix of G, which is A. And also, I want to get G transpose, which is, I'm going to write it here, multiply by the Jacobian matrix of F, which is identity. And then we are just going to copy it back of F and G to make it, this is an X transpose A plus X transpose A transpose. It's an X transpose of A plus A transpose. And this is the total derivative of my function Ex equals to X transpose Ax. All right? And because as I said, someone wants to write it as a gradient form, where the gradient equals to the transpose of the first order total derivative. So they can just write as A plus A transpose multiplied by X. So this one will have the same dimensionality with X. It's an n by 1 vector. And this one is a 1 by n vector. All right? Okay, and I promise you will see such kind of formula in your homework. and lastly, I think I can do a simple example of a spring. If I have a wall with infinite mass, this is how our physics homework always assumes. And I have a point attached to the wall. This is what point? And I assume the rest length of the spring is 0, which means that the spring always wants to collapse to the wall. But I just somehow pull this vertex out of the wall. And by Hooke's law, and I assume the stiffness of the spring is k. It's the constant in Hooke's law, the stiffness constant. And defined by Hooke's law, Ex can be seen as 1/2 of k multiplied by the norm of x squared minus the rest length of the spring, which is 0. 0 is the square root. This is a norm of the vector x and the square. All right. So this is basically the definition of Hooke's law. And also we can write it down simpler because the rest length of the spring is 0. So I can simply write it as 1/2 of k x, the norm of x squared. Also, I can write it as multiplied by x transpose x, because x transpose x is basically the square norm of vector x. All right. So I want to get what is the first order total derivative of Ex near a point A. So because we have the factor rule, this constant can get out of the function. So this is 1/2 multiplied by something, and something is what we just got. Hey. Something is what we just got because we want to get the value of x transpose x, and because we already know the gradient of even more complicated one, x transpose multiplied by a matrix A multiplied by x. So this can be seen as x transpose multiplied by identity multiplied by x. So the first order derivative will be x transpose I plus I transpose. And where I transpose equals to I, so it becomes 2I and canceled with 1/2, it becomes K multiplied by X transpose. And also we know the gradient of E should be the gradient of E is the transpose of the total derivative, so it will be X K. And if you still remember the gravity energy that I took, so the force, the spring force, is a negative gradient of E, so it becomes negative K. It becomes negative Kx. So this is exactly the Hooke's law. If you pull it out for x, if the point attached to the wall is origin, then if I pull the spring to any other point, like this is x, then the spring force is basically pointing to the origin because it's a negative x and multiplied by the constant k. So this is the Hooke's law in force. And we can derive it also from the energy form to the force form.
Maybe you could also mention or remind what is the Hessian.
Oh, right, that's true. Yeah. Yep. And everybody okay with this one? Okay. And lastly, we know that if there is a function of f which is a map from Rn to R, the gradient of f would be another vector, so it will take the input vector x and map it to another vector field. So it will be an Rn to Rn function. All right. If it's a gravity field, I will take x, y, z into the function. So this is function I'm treating the gradient of f as the entire function. And now it's nothing special. You don't need to think about it. It's a gradient. It's just a regular function. And it will maps you to this one, my 0. It's another 3x1 vector. So this is a function from R3 to R3. And similarly, the gradient function is also a function that maps a vector from Rn to Rn, right? So if you're just treating it as a multivariant vector function, we can also get the Jacobian matrix of the gradient. So what is the Jacobian matrix of the gradient f? It will be a n by n matrix, and each, if I write it down, if I also expand the gradient and write it down, it will be partial f, partial x1, partial x1. This is partial f, partial x2, partial x1, blah blah blah, f x n x1. And I can repeat it to write it down to xn, x1, goes back to xn, xn. It will be a symmetric matrix, because the order of taking gradient doesn't matter. Usually it doesn't matter if the function is second order continuous. And we call this matrix, this is the Jacobian of my gradient. And we just define it. Sorry, it's not we just defined it. Someone called it Hessian. We call it Hessian matrix of a scalar vector, of a function f. So if function f is a map from Rn to R, the Hessian matrix will be an m by m matrix. So this is pretty much like the second order derivative of a function in 1D. If I have a function in 1D, the gradient is a slope direction, all right? And the Hessian tells you whether the function is bending towards the negative y-axis or bending towards the positive y-axis. If the second order derivative prime x is positive, it means it's the function is pretty much like a u or like a v character, and it's bending towards the negative of a y-axis. We call it a convex. And if the value of second order derivative of f is smaller than 0, then the function will look like this way. It's bending toward the positive y-axis, and this is a concave. And also in the 3D case, we have the similar analogy. We just called it a Hessian matrix. And it's hard to say if a matrix is larger than 0 or less than 0, but matrix has its own property. If the Hessian matrix is positive, definite, we can write it as H is larger than 0. It's not exactly the larger character. And this is a positive definite, which means that for an arbitrary vector x, x transpose hx will be larger than 0. And also, if the Hessian matrix is negative definite, if it's if it's positive definite, then the function the function of f is a convex. And also, if it's negative definite, then which means that for arbitrary vector x, x transpose hx is less than 0, then the function of f is a concave. So why it's important to say if a function is a convex or a concave? Because it's a very important property in the optimization series. If a function is a convex like this one, it means that for any given region, it has at most one minimum, which is the global minimum of the function f, function x. For example, this one is a convex. Why? Because this function, because this function is f xy equals to x squared plus y squared. It can be written as x, y multiplied by the matrix 1, 0, 0, 1 multiplied by a column vector x and y. All right. So because we know what's the Hessian matrix of this thing, the gradient of fxy, we just get it. It's 1, 0, 0, 1 x, y. So this is the gradient of it. And so we can get the Hessian of f basically in identity matrix. And since it's an identity matrix for an arbitrary vector x belongs to R2, then x transpose multiplied by this matrix multiplied by x will be x norm squared, which is larger or equal than 0. So this matrix is positive semi-definite. Oh wait, and
Yeah,
the-
the trick is
yeah, there's a
zeros
non-zero.
excluded.
Right.
You don't have to wrap up, so.
Yeah. So here that because the definition of a Hessian the positive definite matrix is that for any non-zero vector x, because if it's zero then it's trivial, it must be equals to zero. For any non-zero vector x, then if the form x transpose hx is larger than zero, it's positive definite. So for here, for any non-zero x belongs to R2, this one is guaranteed to be larger than zero. So, which means that identity matrix is a positive definite matrix. And that's why we call this function a convex. And because you know this is convex, we know its minimum point. Where x equals to 0, y equals to 0, this is its minimum point. All right? So I can do it for a really simple change to make a new function. This is if I have a new function f(x,y) equals to x squared minus y squared. It will look like this way. So in theory, it can go down for arbitrary value. If you choose a large enough y, then the function can be arbitrarily small. So it doesn't have a local minimum of the function. Or if you put a region of the function, it might give you multiple local minimums. That's because the matrix, if I expand it up, it will be xy multiplied by 1, 0, 0, negative 1, xy. And we know the Hessian matrix is this one. And this matrix is not positive definite anymore. Because I can choose a vector, there exists a non-zero vector, x equals to like 0, 1, and x transpose h, namely as h, x will equals to negative 1, which means that it's not larger than 0. So this matrix is not larger than 0. So this matrix is not positive definite anymore. So we can't find a global minimum for this kind of function. And another example. Right, so this is the last example. Okay, the last example of the Hessian matrix is a spring. Because we know the gradient of the spring is basically kx. It's a function from R3 to R3. Then what is the Hessian matrix of this attachment spring? So it's the Jacobian matrix of the gradient, all right? So at first, you can tell me what's the dimension of this matrix? It's a R3 by R2 R3 function. Yep, it's a 3 by 3 matrix, and because we know that the gradient of we have know that if f(x) equals to x, the Hessian matrix of it is basically a 3 by 3 identity matrix. All right, so we can use the factor rule to get the k out. The gradient of the entire spring will be k. The Hessian matrix of the entire spring will be k times I 3 by 3. So if I expand it out, it will look k, 0, 0, 0, 0, 0, 0, 0. So this is the Hessian matrix of the spring, of this attachment spring. And because this one is k times identity, as long as k is a positive value, this matrix is going to be a positive definite matrix, which means that the system has a minimum energy. And it's obvious where if I put it back to the origin, the system achieves its minimum energy. That's a good property of our convex function. All right, so I think I can finish it. This is our first linear algebra class. If you have any questions, the Piazza is already on. You can just log on there to make questions. I'm not sure if
don't be fooled. The homework is not 0 rest length spring, so it's not that simple. It's not that complicated and not this simple.
Yeah.
Can you post your notes on Canvas or something?
Right, and it's been recorded, so we will probably also put this on YouTube, and you can always review that.
Excellent, thanks.
Thank you.
Yeah.